In this problem, we're looking at some normal modes on a string that's clamped at both ends. We're given the linear density of that string in grams per meter, and we want to convert this to SI units, so I'll just do that up here. We normally use the Greek letter mu for this, so we have to shift the decimal place 3 times, and I end up with 0.0058 kilograms per meter. That will be useful later. We're told the entire length of the string is 2.5 meters. And we're given 2 different normal modes here, and one of them is the 4th harmonic. I see 4 antinodes, and I can call this F4. It's a frequency of 192 hertz, giving me the 4th harmonic on a string of length 2.5. We're given a second normal mode, and it has 5 antinodes, so that's F5. So we observe these 2 resonances, one with 4 antinodes at 192 hertz, one with 5 antinodes at 240 hertz. And we're asked a whole series of questions here. First, I want to get the fundamental frequency, in other words, the frequency of the 1st harmonic. And we actually have more information than we need, but we'll go ahead and use the extra information to check our work. So what I'm going to use here is this formula for the nth harmonic in terms of the 1st harmonic. And it turns out to be this simple. The nth harmonic is n times the 1st harmonic. And I'll post a link to the video where that was derived. So for example, I could take the 4th harmonic here and say that F4 is equal to 4 times the 1st harmonic. Well, then all I have to do is solve for the 1st harmonic. It's 1/4 of the 4th harmonic. In other words, it's 1/4 of 192. And when I divide that, I get a 1st harmonic with a frequency of 48 hertz. Now again, this problem comes with extra information. We could have done exactly the same calculation with the 5th harmonic. So I could say that my 1st harmonic is 1/5 of the frequency for the 5th harmonic. That would be 1/5 of 240, and I get the same 48 hertz. So that's a nice check on our work. In part B, we want the wave velocity. So what we're using here is the basic wave speed equation V equals F lambda, the frequency multiplied by the wavelength, and I'll post a link to the video where that was derived. Again, we have a choice here. We can use either one of these normal modes to compute the wave velocity. The easiest one to use is the 4th harmonic, and it's because the wavelength is very easy to see here. I have 2 wavelengths on a 2.5 meter string. That means my wavelength is going to be 1/2 of 2.5 meters, or 1.25 meters. The frequency that gave me that wavelength was 192 hertz. So I plug into the wave speed formula, and I have 192 hertz. And remember here, if you're curious about the units, that a hertz has units of 1/seconds, oscillations per second. And I multiply that by my wavelength of 1.25 meters, and I see that I get units of meters per second. So this gives me a wave speed of 240 meters per second. Now you could do exactly the same thing with the 5th harmonic. It's just that the math is a little bit trickier. In that picture, I have 1, 2.5. 2.5 wavelengths equals 2.5 meters. So I'll go ahead and subscript these. Lambda 5 is what I'm looking for here, and I have 2.5 complete wavelengths. So 2.5 lambda 5 is equal to 2.5 meters. So lambda 5 is equal to 1. That happened with a frequency of 240 hertz. So the wave speed, just as a check on our work here, V equals F lambda, 240 hertz times 1 meter gives me the same 240 meters per second. So that's good. Finally, we want to get the tension in the string. And we have a formula relating the linear density of the tension in the string and the wave speed. And that's the square root of the tension divided by the linear density. To get the tension out of this, I square both sides and multiply by the linear density. And I have T equals V squared times mu, the linear density. All we have to do is plug in our wave speed of 240. I get 240 squared. Our linear density of 0.0058 kilograms per meter. And I get a tension of 334 newtons. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.